Section 2.3, we are going to look today at other set operations. There's several that we're going to look at. Two that are going to be like super important to us, and another one that we're going to dabble in just a little bit. The first one we're going to look at is called set intersection. The intersection of two sets is a set of all elements that are common to both sets. Sometimes our math language and our English language, and you guys know what I mean, don't match up very well. This is not one of those cases. It's really good. When we talk about an intersection of the streets, this is exactly what we mean. So if I were to talk about the intersection of Kickapoo and MacArthur, you would know that that's the part that they both cross over at, right? It's not just a little bit off of the intersection. It's not Brahms, and it's not Stavros Hall, and it's not that old bank building or the CD warehouse. It's the exact part where they cross, right? So a set of intersection, just using some of the notation that we're learning, is the set of all x such that x is in A and x is in B. And the way that we notate that is we have an A and we have a B, and it's an upside down U. Kind of looks like an N for intersection between the two. Okay, what they have in common. A union. A union of two sets is a collection of objects that's in one set or the other set or both. So, let me write my math lingo and then I'll give you a concrete example where we see this happen as well. X such that X is an element of A or X is an element of B. And in math, when we use or, at least for the case of what we're doing right now, it's not an exclusive or. It's not this or this. They can also be in both. Okay, both is included in this. Write that down if you need to remember that. And the symbol between them actually looks like a U. U for union, and it looks sort of like an N for intersection. And a really, really great visual example, and I would encourage you to write this down, is what we mean by the union of marriage, right? When two people get married, you get all my stuff and I get all your stuff, right? If you've got college loans, they're coming part of my loan debt now, right? If I have kids, they're now yours too. You have a responsibility here, right? And the two shall be one, just like the minister says. That's a union. You get all of it. The good, the bad, everything. Yes?
When writing the U's, is there a way we can write them to make sure you can tell? Because when I write normal U's, I don't put that line thing. They look exactly like it.
Well, for most of the time, this is going to be anytime we're talking about a union, it's going to be sandwiched between two sets. Whereas if we were talking about a universal set U, it wouldn't be between the two sets. This is sort of like when you put a plus sign between something. Plus doesn't make any difference. I mean, you wouldn't just write this out here and expect somebody to add something together unless there's numbers on either side. It's the same thing in this, okay? So unless you've got the set on either side, it's not going to be talking about a union anyway. So I think that'll probably be enough of a difference that we'll be able to keep them straight. Okay, so we're going to do an example. Oh, no, I have one more. I'm sorry. There is one more. We don't see this one used quite as much, but these two we see used a lot, okay? Union, intersection, there are predominant ones we're going to use. The third one that we're going to see used occasionally, it's not super common, is called a relative difference. This is the set of all elements in one set that are not in the other set. Okay, so the notation for that in set builder notation is this is all the x such that x is an element of A and x is not an element of B. And notationally, this looks like subtraction. A minus B. Okay, so we take all the stuff in A and we remove. We physically remove something from it. Okay, I want to go back to each of these three and I want to show you what it looks like in terms of a visual. Okay, who's a visual learner in here? I am too. I think very visually. I was involved in a program when I was a teenager. My daughter's involved in it now. And if I could see the picture, right, as I studied, I would remember where it was on the page. That's how much of a visual learner I was. My daughter, she listens to the same thing on like CD, and she remembers what she hears. She's an auditory learner. So a visual learner, this will be something that will be something maybe useful or remembering, helpful for you to remember. Okay, so we talked about Venn diagrams briefly last time. I want you to draw a rectangle, either out to the side or something like that of the particular sets. They don't need to be big. And I want you to draw two overlapping circles. Oh, that was way too thick. Let's try that again. Two overlapping circles inside of your rectangle. And they don't have to look super circular, okay? There's nothing special about the shape. I want you to label one of them A, and I want you to label one of them B. And this is the same picture you're going to draw on all three of these diagrams to start with. So repeat this picture for union. To make mine a little smaller because I don't have as much space. And then here's my one for relative difference. Okay, they all look the same so far. Okay, so looking at the first picture, we're going to shade in the part that's the intersection. And we know the intersection should be what they have in common. So where do you expect that I'm going to shade? And that little moon shape, that little half kind of oblong, it looks like a football, right? Kind of. And my shading's not perfect, but you have the idea. It's the part where they overlap. That's the intersection. Okay, union says, I get it all. What's yours is mine, what's mine is yours. Where do you think I would shade visually for the union of these two sets? Everything in either circle. What about the overlap? Do I get to shade that too? I do. I do. So my shading's really broad for this one, right? I get to shade everything in A and everything in B like this. Okay? And then relative difference is our last one. Relative difference should be everything in A that's not in B. What's that going to look like visually? It's going to kind of look like what happens as the moon begins to, I can't remember if it's wane or wax, whichever one it's where the moon, goes away. Is it wane? Okay. So it's going to look like the part of A that doesn't overlap B. So this piece over here, right? That would be A minus B. Okay, the relative difference of A and B. And we can do the same thing with B minus A, right? It'd be the other part over here on the side. All right, we're going to do now a concrete example with like elements, and we're going to do people. We have Mary and Joe. No, Mary and Mark. Mary's mother to Mark. Joe. Yes, Mary and Joe. I said it right the first time. Okay. Oh my goodness. Consider Mary, single mom to one child, Mark, and Joe, single dad to two children, Jack and Jill. Mary and Joe get married, and together they have two children, Anne and Andy. If M represents Mary's kids, and we're talking biological here just so I can make a concrete example, okay? So please don't tell me that they're all kids. I agree with you, okay? But for the sake of what we're talking about like genetics, okay? M is Mary's kids genetically. J is Joe's kids genetically. We're going to find and describe each of the following. So, what would M intersect Joe represent? Yeah, the kids they had together. Right? Biologically together. Who would that be in our example? Yes, Anne and Andy. What would the union represent? All of them. All of the kids. This is like, you know, the family picture that goes in the church directory or something like that, right? The picture you send out on your Christmas card. This is the union. And that would be who? Mark, Jack, Jill, who else? And Anne and Andy. What would M minus J, right? Relative difference. Who would that be? Not who would that be. What would it be like description-wise? So Mary's, I like your word just Mary's kids, right? For the sake of our argument, this would be the kids that she actually physically gave birth to, right? I mean, the way we've described it. Yes, Allison?
So up there it says that Joe is the single guy with 2 children, and then the J is Joe's kids, but isn't Annie and the kids they had together and not his kids?
This is before they got married.
Okay.
Yeah, before they got married, they each had individual children they brought into the marriage, and then they got married and they had more kids together. Does that help?
Because like probably overthinking it.
Huh?
She said the U was the union, like marriage is a union, what's yours is mine is ours. So like when they're married, they have all of the kids, all kids are now theirs when they're married.
Right.
The U is for union.
U is for union. It's the family picture, right? Who gets to be in the family picture? Well, everybody related to Joe or Mary.
So was Anne and Andy the 2 kids they had together, or
Yes.
the kids he had before marriage?
Anne and Andy are the 2 kids they have together. It's what it says. Together they have 2 children. Right? Single dad to 2 children, Jack and Jill. Joe has Jack and Jill, and then he marries Mary, and they have 2 more kids, Anne and Andy. Okay? All right, C was just Mary's kids. That was the way, I think Shelby said the word just. I liked that. Just Mary's kids. So which ones are just Mary's kids, as in she biologically gave birth to them? Mark.
Wait, is it Anne? It wouldn't be Anne.
It wouldn't?
She gave birth to Anne and Andy, so they are her kids. Right, but they'll be ours.
Oh, yes, so you're right. The ones that are just Mary's kids would only include Mark. Thank you for clarifying. I probably said that funny when I was describing it. Thank you for clarifying. Yes, the ones who only belong to Mary are just Mark. Just Mary's kids are Mark. Is Mark. Yeah. Okay. Now, we almost have used this. We just haven't said that we've used it yet. These are commutativity and associativity properties of these sets. So the commutativity of set intersection and set union. If I were to take, we'll say it this way first. For all sets A and B, A intersection of B is the same as B intersect A. Right? Like if I talk about the intersection of Kickapoo and MacArthur, and Mackenzie talks about the intersection of MacArthur and Kickapoo, we're talking about the exact same place, right? There's no difference. If we talk about the union of Mary and Joe getting married, yeah, they're the ones who got married, or we talk about the union of Joe and Mary getting married, we're talking about the same collection of stuff. Kids in this case. Same group of kids, right? Same group. So the order of these things doesn't make any difference. Now, we have mentioned this sort of in passing before that, you know, some things work this way, like addition works this way, right? 5 plus 2 is 2 plus 5. But not everything works this way. 5 minus 2 is not 2 minus 5. So this is not necessarily something that we should be like, well, of course it is. It's always like that. Well, it isn't always like that, but it is for unions and intersections. Okay? We also have associativity. So for all, again, this is, well, you know what? We'll do it this way. This is still for all sets A and B. But now we need a set C as well. So for all sets A, B, and C, A intersect B intersect C is the same thing as A intersect B intersect C. And unions are the same. A union B union C is the same thing as A union B union C. We haven't actually used 3 sets and talked about what that looks like visually, but we will before this particular lesson's over, although it might not be before today's over, okay? We will look at what happens with unions. I can't remember where it falls in this lesson, or at 3 sets. And then we're going to take a look at distribution. Okay, so let me show you what distribution is talking about. If we have A intersect B union C, this is the same thing as A intersect B union A intersect C. Like I said, we'll explore the properties of this and how it works in terms of Venn diagrams, and you can see that they actually work when we get to groups of 3 sets. All right, our last sort of definitional thing for the moment. I am going to prove this one. It's called the cardinal number formula. If I want to find the number of elements in a union, we're going to break it apart into pieces. So we drew a picture earlier, so I'm going to draw that picture again of union. Here's A and here's B. And visually we had this thing going on, right? Everybody good with that picture? So if I talk about the number of elements in a union, and I say, well, I really just need to take the number of elements in A, and I'll shade that in yellow, and I'll add to it the number of elements of B, and I'll shade that one in blue. What do you notice happened? There's a rainbow, but besides that, it's beautiful. What happened in the middle, Shelby? It made green in the middle. How did that happen, though? Ooh, so I shaded the middle in 2 colors, right? I shaded it in yellow, and I shaded it in blue. So I shaded it twice. So I sort of listed it twice, right? Like if I were listing out elements like the ones on the board behind me here, I would have had to actually list things twice, right? Things would have gotten double counted. It's another way to describe it. So I need a way to sort of remove the things I double counted. What's another way of describing the part in the middle where they overlapped? It's not the union, it's the intersection. So when I'm counting things, if I decide to count the number of elements in each set individually, I have to remove the fact that I double counted the intersection, right? Because I shaded it both in yellow and in blue when I was shading. I double counted that part in the middle. So this is called the cardinal number formula. It kind of feels like, wait a minute, shouldn't I be adding the number at the end? And the answer is actually no, because the number at the end was counted twice when you counted the individual sets. All right, we're going to talk about the Cartesian product. This one doesn't come up very much. It is mentioned. The set of all ordered pairs such that the first component comes from the first set and the second component comes from the second set. And the easiest way to describe that or to show that is to actually create some sets with some elements. So jot in, I think there's like 5 different blanks. How many blanks do I have? 5 blanks write those down. And then we're going to do an example with A, where A is X, Y, and Z. And set B is 1, 2. Okay. A is X, Y, Z, and B is the numbers 1 and 2. It's just a collection of objects. Okay, so a Cartesian product is similar to what happens when we do like the Cartesian plane, right? Your XY ordered pair plane. You pair up an X, you pair up a Y, and it pinpoints a point on the plane. Okay, same idea as that. The way we represent it is we represent it to look, it kind of looks like multiplication, A cross B. And it's going to be a collection of ordered pairs, points, right? Like X, Y in an ordered pair in the plane. We're going to take an object from set A. Well, we'll just take the first one. And we're going to pair it with an object from set B. And we'll just pair it with the first one. So one of our objects in our Cartesian product is the object X, 1. But I didn't have to pair up X with 1. I could have paired up X with 2. But I didn't have to use X, as my object at all. I could have used the object Y and paired it with 1, or I could have paired Y with 2. Now, this isn't one-to-one correspondences, although it feels a little bit the same. But I could have selected Z and paired it with 1, or Z with 2. And the collection of all such pairings is the Cartesian product. Now I'd like for you to notice something. We can count the number of objects here. And I will write it down. I want you to be very careful. The Cartesian product is the set of ordered pairs. But I can count the number of objects in each of these as well. The number of objects in A, the number of objects in B, and the number of objects in the Cartesian product. How many objects, how many elements did we have in set A? 3, I think, right? X, Y, and Z. So 3. How many elements were there in set B? 2. How many elements were there in the Cartesian product? 6. Remember, an element there is actually an ordered pair. Do you see anything that you could speculate is happening between all of these numbers over here on the right? 3 times 2 equals 6, right? It's much like the fundamental principle of counting that we were working with for our one-to-one correspondences and things like that in the last section. So that does in fact happen. It's another formula. The number of objects in A times the number of objects in B will be the number of objects in the Cartesian product. Okay, that is a true fact. If you're asked to find the number of objects, you are just multiplying. If you're asked to actually find the objects, you're looking at the ordered pairs. There's a different question there, right? What am I asked to find? Am I asked to find the number of objects, or am I asked to find the actual objects? So on the left-hand side, we're asked to find the objects, the elements. Over here, we're talking about the cardinal number. Okay. All right, we're going to do at least one example before we quit today. I think we have time for 2, though. We'll see. And they're going to use the Venn diagrams, and then we'll get back into Venn diagrams a little bit more next time. So far, all I feel like I've done is just given you a whole bunch of new vocabulary with a whole bunch of word pictures, and haven't really shown you what we can do with them. Okay, so that's what I'm going to do. The first thing I'd like for you to do is I'd like for you to draw a Venn diagram. And because the Venn diagram says, or part A here says A and B, we're going to draw 2 overlapping circles, A and B, in our Venn diagram, okay? So 2 overlapping circles, label them A and B. And U is the universal set over here on the outside. Now, in full disclosure, there is more than one way of doing what I'm about to show you. However, I'm going to show you a specific method that I would like you to use. And the reason is because as the diagrams become more complicated, other methods that you might be tempted to use will be less effective. They'll be a lot more difficult to actually use and to use them right. Okay? So I really do want you to use the method that I'm showing you. The method I'm showing you is that we're going to number our regions. So this is going to be the number 1. My overlap is in 2. The area on the outside is in circle B is in 3. And then the number 4 will be on the outside of the rectangle. Well, in the rectangle outside the circles. Okay, so there are 4 different regions here, right? If you were wandering around aimlessly inside of the rectangle, you would be in one of those 4 locations. Agreed? Okay. So what we're going to do then is we're going to look at the objects that we're given right here, and we're going to describe them in terms of the numbers that are in their regions. So this has an A with a bar on the top of it. What does that bar mean again? It means what? Not. Did somebody say not? Is that what I heard? What did you say, Nicole?
I said not. She said
Not. What did you say? Say, Veronica. It's okay. Complement. Those are both different ways of saying the same thing. So you're both right. There's something that's said as not A or the complement of A. Okay? So when I put a bar on top of something, it means the things that are not in that. Okay? So I still have to be inside of the rectangle. That's non-negotiable. Okay? Sort of like, like mom locks the doors of the house and the question is what room you're in. There's no question. You're in the house. The doors are locked. Question is what room. Okay? So we are definitely inside of rectangle U, but we are not supposed to be in A. So where could we be? Which one of these numbers could we be in terms of the locations? 3 or 4. Can't be in 2 because 2 is in circle A. Okay? It's the overlapping part, but it's still part of circle A. We're going to do the same thing with B because that's what the problem says. B complement or not B. So which numbers are not inside of circle B? 1 and 4. Okay, everybody good so far? The whole way of showing the work for this is listing out numbered regions. Now, how does it say that these two are supposed to be related? Union. We need the union. A complement, or not A, union not B. Okay, so these are our objects, 1, 3, and 4. And we need the union of 3, 4 with 1, 4. What does union mean? All of them. What's yours is mine and mine is yours. When I'm doing a union, I get everything. So I'm going to list what numbers? 1, 3, and 4. Okay? But now I need to go back to the question and do what it told me to do. And it told me to do what? Shade the diagram. So what do you think I'm going to do? Shade 1, 3, and 4. So back in my picture, I'm going to shade region 1, region 3, and this big outer region 4. Okay? Shading the diagram to go with my numbers. We're going to draw the picture for the next one. We're not going to get to the shading because I said we had 3 objects and now we do. And I haven't drawn you a picture with these 3 objects yet, so that'll be a good place for us to stop. You need a rectangle that almost looks squarish. It needs to be big and fat. You need 3 overlapping circles. 1, 2, 3, and it starts to look like what object is familiar to you. It hasn't been that long. Okay. Something else I was thinking of. Maybe the Olympic rings? Oh, yeah. There's only 3 of them and not 5, but yeah, okay. All right. Label them A, B, C. And then the union's out here. How many regions are there? Count. Close. 8. You probably forgot the outside rectangle part, Sally. So as we number our regions, the way you usually see them numbered is straight across the top and then through the middle, on the bottom, and then on the outside. Those are my 8 regions. Now, B is not a very good example for how I'm about to do the problem when we come back next time, because there's an easier way to do it. But if we had more of the complements on top of things, if we didn't have the union and the intersection arranged just so, it becomes more complicated much more complicated more quickly. That's what I wanted to say. Okay? So we're going to identify all the numbers. We're going to match them up with unions and intersection. And in the very end, we will shade the diagram much like we did on the previous problem.